Good morning, everyone, and thanks for joining me on this session on Spark. I hope you all had a good conference and a great replay party. So as you head back, we want to leave you with some of the enhancements and improvements that we have made on the Amazon EMR service to really accelerate your Spark workloads. So that's what this session is going to be about. My name is Radhika Ravirala. I'm a product manager at AWS with the Amazon EMR service team, and my colleague Neil couldn't be here. But together, we want to walk you through some of these enhancements as well as show you what you can expect out of Amazon EMR as you begin to try out some of our preview features as well. So let's start by looking at some of the key benefits of EMR. So EMR makes it really easy for you to run Spark as well as other open source projects such as Apache Hive, Apache Presto, Flink, etc. on the platform. So EMR comes with the latest OSS frameworks, and within 30 days of the new release from the open source community, you can expect to find that in Amazon EMR. And we also package related frameworks that help you build big data applications. And those include projects such as Apache Hudi, etc. And we'll talk about Hudi in the later slides. So EMR gives you the best performance at the lowest cost. And we enable this because we are able to offer customers an ability to run your EMR workloads on Spark instances. On top of that, we have worked on the enhancements to the runtime environment, which resulted in the performance that is 2 times faster than the open source. And when you leverage the fastness with the EC2 Spark instances, as well or reserved instances, if that is your case, then you can really get about 50 to 80% cost reductions in running your big data processing workloads on EMR. EMR is optimized for Amazon S3 as a data lake. We have seen a number of S3 data lakes that are empowered by the processing provided by EMR. So data lakes are a very common architectural pattern these days, where you get all the benefits of S3 as a storage layer, and by decoupling the storage from the compute, which is the EMR here, you are able to process a large amount of data and provide access to a variety of use cases from your data lake. So EMR is a fully managed and easy to set up, which means that you can get started with just a few clicks on the console or just by running the CLI commands. We enable you to spin up cluster within minutes and scale these clusters as your workload changes. So when we begin to think about how organizations have been using Amazon EMR, we need to go back to the key personas in a typical organization. So for example, you have Maria, the data scientist, Anna, the data analyst, Richard, the data engineer, and Carlos, the administrator. So how does Spark on Amazon EMR empower these personas? So let's take a look at what a typical data engineer and a data analyst does on a daily basis. A data scientist spends a lot of time building and training ML models. They also perform interactive data analysis in Jupyter notebooks. And the analysts, on the other hand, they prepare reports based on some kind of data analysis. So they do perform ad hoc analysis by running a lot of SQL queries and prepare these reports. Now, Anna and Maria really would like their interactive analysis as well as machine learning pipelines to be as simple as possible. So let's take a look at how Amazon EMR helps in that simplification. So as some of you might know, we have Amazon EMR Studio. We launched Amazon EMR Studio which is a integrated development environment, IDE, that reduces the time for your data scientists and data analysts to build and deploy your Spark applications, as well as run your data processing workloads. It's a fully managed application with a single sign-on, Jupyter notebooks, automated infrastructure provisioning, as well as job diagnosis. So it is very easy to get started. You can use your single sign-on method, or if you have a corporate identity, to directly log into your notebooks instead of going to the AWS console. But if you're already on AWS and you would like to use IAM, that is also possible with Emr Studio. You and your team can log into the Amazon Emr Studio directly through a secure URL to manage your notebooks using your corporate identities via SSO. There is no need to log into the console if you don't wish to do so. And it's a completely new experience with multi-tenant studios where multiple users and groups can log into the same studio. And we'll learn more about this in the later slides. The other aspect about Emr Studio that is super helpful to the scientists and engineers is that you can develop, visualize, debug, and optimize analytics and machine learning applications very easily. So Studio is like a comprehensive tool that provides a fully managed notebook based on Jupyter Lab. It gives you the flexibility to create notebooks independent of the clusters. So that means you can get started with a notebook, you start coding, and then you can attach your clusters at a later time. So you can attach and detach notebooks to and from these clusters using a single click. You can also provision EMR clusters using the cluster templates that are pre-configured by your organization. What that means is if you have some standard template that your organization wants to use for launching your EMR clusters, you can use that with Emr Studio. You can also collaborate with your peers by sharing notebooks through either GitHub or AWS Code Commit and Bitbucket. So you can collaborate with your team and analyze data from the data lakes using PySpark, Spark SQL, Spark R, and Scala. So Studio integrates with Code Commit, GitHub, and Bitbucket so that you can work with the rest of your team. And you can also import custom Python libraries like Pandas or NumPy and install them directly into your notebooks. So we'll learn more about this again in a couple of later slides. So to understand how Emr Studio enables your data scientists and data engineers, so let's take a look at a typical workflow for a data science or an analyst. So a data science workflow begins by prototyping code. And here, before you can prototype code, you need to log in to a Jupyter notebook. And in order to do that, you can do that with your corporate identity if you already have Okta or Auth0 in your organization, or you could use IAM, which is a new support we enabled for authentication recently. And then you can get into the Studio environment, which gives you a completely managed notebook. And what that means is it gives you a notebook where you can organize your notebooks in such a way that your teams can collaborate on common projects together. So Emr Studio has this concept of workspaces. And the workspace is a construct that will help you group some of your notebooks based on some common attributes they have, such as compute and storage. You can group them by that and organize your notebooks so that they are not cluttered. And they have similar properties, as I said. For example, you can create workspaces and specify all these all the notebooks within this workspace to use a specific S3 buckets as a storage location for those notebooks. So if you have team A building a set of notebooks and you want all the members in the team A to persist their notebooks in a single S3 location, you can create a workspace to do that. You can attach your workspace to a cluster. All the notebooks in the workspace are attached to that cluster. And similarly, for a Git repo, when you link your workspace to a Git repository, all the notebooks in the same workspace are automatically linked to that Git repo. So this enables a lot of collaboration between the teams and helps you manage your notebooks in a much sane fashion. So in this fully managed Jupyter notebook, you can write code in Python, Scala, R, as well as PySpark. So this is how the EMR workspace looks like. It's a single IDE for interactive data analysis, and it goes beyond the standard Jupyter to give you the single IDE for data analysis as well as launching clusters. So the concept of workspaces exists in the open source project called Jupyter Lab, and we have extended that concept to include additional features to give you a broad set of capabilities to run everything in your studio. So all the controls are on the left-hand side, and you have a launcher tab to launch notebooks and other extensions from this console. So once you prototype the code, you want to load some custom kernels or custom libraries. So it is very common for the data scientists and data engineers to load some data science packages like NumPy, Pandas, or even something that they have built. So in order to do that, in the prototyping code, you can load custom kernels and libraries directly into the notebook. And so you can install the notebook scope libraries with PySpark, for example, with the Spark kernel. You don't need to rely on any bootstrap action. So previously, if you remember, we have had a lot of customers install packages directly on the cluster through bootstrap actions in order to have those packages available in your notebooks. So customers who have seen EMR notebooks before, this was the experience. And then we introduced the concept of notebook scoped libraries where you don't need to do this step. So this is a runtime installation of packages that you can do when you're creating your notebook. So you can import your favorite Python libraries from the PyPy repo and install them on the remote EMR cluster on the fly. Now there are some interesting aspects to this feature. So the libraries you install are instantly available to your Spark runtime environment. There is no need for you to restart the notebook or notebook session or even recreate another EMR cluster. So another good thing about this feature is that there is something called dependency isolation. And what that means is the libraries that you install are isolated to your notebook session. And they don't interfere with the bootstrap cluster libraries or the libraries installed from other notebook sessions. So if you have a bunch of developers installing different libraries, they all have isolation from each other. And the libraries that you install take precedence over any bootstrap libraries that you launched with the cluster launch. So that's another thing to remember. And multiple users can choose their preferred version of the Python library. So if you have developers working with different versions of the library, they can all install their own version. So this feature also enables a portable library environment. The package and the library installation all happens in the notebook file for you to create these library environment, which means that you can reuse this library environment for later notebooks that you will launch. And lastly, the installation of the additional Python libraries and kernels are done on the leader node of the EMR cluster, and that's how we are able to enable this multi-tenant nature of installing packages that are custom built for individual users. And then once you install your favorite kernels and packages, then you want to collaborate. And that is enabled by connecting to AWS Code Commit, GitHub, or a Bitbucket. And you can choose existing Git repos, or you can create new. So this is something that allows you to create your notebooks, upload them to your Git library, and then access them from the comfort of your Emr Studio notebook. So once you, your Git repo has your notebooks, you want to run your notebooks on a small cluster to test them out and see how they work. And when you do that activity, you will want to make sure that you have the ability to debug should something go wrong, right? So with a single click, you can attach your workspace to the cluster to run the jobs. And we provide you with several options here. First, you can attach the workspace to an existing EMR cluster. And then once you start running, you have the ability to debug your applications very easily. So you provision EMR clusters using simple configuration, and you can limit the users to either the cluster templates or creating their own Amazon EMR clusters. And what that means is when you are creating EMR clusters, you can ensure that that cluster has a limited number of cluster templates. And you can, if that cluster template doesn't fit your need, you can go ahead and create your own cluster. And it's not just EMR on EKS. From your notebook, you can connect to the clusters that you have pre-created, the clusters you want to launch new, or you want to connect to clusters from EKS. So as many of you know, we have another deployment option called EMR on EKS. And you can choose an EMR on EKS cluster as well from the console. Another beauty is that you can detach and reattach these notebooks to any cluster of your choice. So for example, you might be running your notebooks against a cluster with EMR release 5.33, and later you want to test that same notebook against the latest version. So you can go and when we release 5.34 or the release 6.4, you can go and test the same notebook with that release by simply attaching your notebook to that cluster. And so next comes the debugging part. So live debugging is very simple. And when you run your Spark application in your notebook, you can debug the code by simply selecting the Spark UI link. So as you run each cell, we have the Spark UI available in the console itself, and you can click on that link, and that'll take you to the Spark UI to navigate and to look at how your job is executing. So how much memory is allocated, how the DAG is created, and so on and so forth. You can also view the debugging information in Spark History Server for application in a separate browser tab. So if you're interested in the completed jobs, or if you're interested in looking at the history server, the Spark History Server, we have that capability as well via another link on the notebook console. And finally, once you are happy with your notebooks, you have tested it thoroughly with different versions, and you're comfortable moving it to the production, you want to be able to build pipelines. So you want to be able to execute these pipelines, the notebooks that you have created, in an automated fashion using either Apache Airflow or the managed version that we offer, which is called the Amazon Managed Workflows for Apache Airflow, and as well as step functions. So you can run the notebooks as a pipeline using the orchestration services that you're already used to, And one other thing to note here is that you can parameterize and chain your notebooks that can be run in this pipeline. So you can change the parameters with each run. And finally, you want to monitor your production pipelines. Emr Studio enables that by letting you browse all the clusters in one location. So you can narrow down the clusters for your investigation, and then using filters such as the cluster state, and monitor how your jobs are running on that particular cluster. And when you run your EMR application, the logs are automatically uploaded to S3. So you can still access logs on the terminated cluster. So if you have attached your notebook to a cluster that was later terminated, the logs are still available. You can diagnose the jobs on both active and terminated clusters using native application UI such as Spark UI, Yarn timeline service, as well as the test UI. So you can overlay the execution context on the jobs even for the terminated clusters, and the jobs for this makes it easy for you to traverse very easily through on the notebook console itself and look through the clusters to find the one or identify the one you're interested in monitoring. So this is a quick summary of the Studio features we released in 2021. So we support IAM authentication and federation as well. So previously we only supported AWS SSO. So for those of you who have used Studio earlier, you will notice that we have IAM now. You can also write Spark SQL, Spark R, Scala, and PySpark cells within a single notebook. And this is again an important enhancements that we have added to the Studio because we have a lot of customers who want a functionality where you can run different queries in different cells. So the OSS Jupyter does not support this feature, and our customers asked for this, and that's why we built it or embedded into the EMR Studio. You can also auto-terminate EMR clusters that are idle and save on costs. You can do real-time co-authoring of your notebooks, as we spoke earlier. You also have fine-grained access control through lake formation, which is currently in preview. And we ask you to stay tuned for more on EMR Studio. So who exactly is using EMR Studio? So here is a quote from one of our customers, Verana Health. And in Verana's use case, they had their notebooks that were cluttering their environment. And once they started using EMR Studio as the official workflow for their Jupyter notebooks, it has helped them to reduce costs as well as time spent supporting the users on those notebooks. Another customer that has been successfully using EMR Studio is Mapbox. And in Mapbox case, they have been using EMR Studio to run prototype Spark applications as well as data science models that power their larger processing frameworks. So the integrated environment makes it easy for their data scientists to quickly develop the prototypes, test them out before they push them into other production pipelines. And so for those data scientists who are deep into machine learning, SageMaker, our end-to-end machine learning platform, is a fantastic choice. For those working with SageMaker Studio, integration with EMR is a new capability that we built in. And what it allows you to do is process petabyte scale data sets easily using EMR from your SageMaker Studio. We have seen customers adopt this model even previously before we had SageMaker Studio, but they had to configure their SageMaker environment in order to connect to the right cluster. But now, with this deep integration, it's really a matter of a few clicks. You can use the EMR native integration with EC2 Spot instances as well as the Graviton instances to run large-scale data processing at lower cost. So this is, again, very much in the realm of what a data scientist does, especially if they're using tools like SageMaker Studio. So some of the benefits that you get with this deep integration with SageMaker is that we already spoke about discovering and connecting to EMR clusters from your SageMaker Studio itself. And in addition to that, you no longer are restricted to just running Spark applications, right? You can run Hive, Presto jobs as well on EMR from the SageMaker Studio. That's another neat feature that a lot of data scientists appreciate. And a lot of them have familiar tools such as Spark UI for debugging or using Tez's UI to look at the Hive jobs. And you can continue to use them when SageMaker Studio, with SageMaker Studio integration with EMR. And not just that, you get the benefits of EMR out of the box, right? You create and scale and auto-terminate EMR clusters using AWS Service Catalog templates. So what this means is from the studio itself, you can launch these clusters and auto-scale them as you need, as well as auto-terminate them when they're idle or not being used. So now that we have walked through a workflow for a data scientist and a data analyst, now let's look at how EMR, Amazon EMR, helps the data engineer in their daily tasks. So a data engineer is typically responsible for building and deploying data pipelines. And when it comes to pipelines, there are a number of orchestration options. So if you look at the data engineering platforms, they continue to evolve. So every year we see a new pattern. But there are a couple of common patterns that we see more and more. And that has to do with running edge nodes for your EMR clusters or running notebooks that interact with your EMR clusters. And so once you have a need where you need to run your jobs in an automated fashion using some kind of an orchestration tool, EMR already has been supporting running your orchestrated pipelines through Apache Airflow as well as step functions. When we released Amazon Managed Workflows for Apache Airflow, we have seen customers adopt the managed version of Apache Airflow as well and submit jobs to their EMR clusters using Amazon MWA. And step functions is a favorite to a lot of EMR customers because it is a serverless service that helps you orchestrate your EMR jobs very easily. It has deep integrations with other data processing services on AWS. And if you're running or using multiple services in addition to Amazon EMR, you can use step functions to orchestrate your entire pipeline. So step functions actually submits the jobs and push and pauses until the task completes on EMR. So a data engineer also wants a performance optimized runtime. And what that means is Spark jobs are notorious for their memory issues. And a lot of times you have data engineers spending a lot of time trying to understand how they can improve the performance of Spark on their Hadoop environment. And so we have differentiated Spark runtime performance on Amazon EMR. The primary tenets we have here are we do not want to break the API compatibility. So just because we are working on enhancements on Spark, we do not want to break the API compatibility with open source. That's a primary tenet for us. And the second thing is the performance improvements are out of the box. So you do not have to pay extra to get those performance benefits. So Amazon EMR provides multiple performance optimization features for Spark. So with Spark on EMR, you can get over 2 times faster performance than the open source framework. So we did a TPCDS 3 terabyte benchmark and compared that to the standard Apache Spark. And that's where we learned that we get the much faster performance than the standard Apache Spark 3.0 from this derived TPCDS test bench that we ran. So in order to bring out these performance enhancements, we have implemented a number of features within the Amazon EMR service that helped accelerate the Spark for performance. For example, we have dynamically sized executors. We'll learn more about this in next slides. We have adaptive joint selection. There is dynamic pruning of some data columns. There is operator optimization. So all these are under the hood optimizations that we have implemented so that you get the benefits of running a optimized Spark version on Amazon EMR. So here is an example of one such enhancement. So let's talk about right-sizing executors. So one of the primary recommendations we have for customers is to right-size their executors to tailor to their workload. And this is hard because you need to specify the executor size to fit the smallest instance. And this is because customers tend to use a diverse set of EC2 instances with Amazon EMR. Because Amazon EMR supports that, and we even encourage customers to run a diverse set of instances from different families, it's always hard to right-size the executors because the executor size that you've chosen should fit the smallest denominator or the smallest instance that you have in the pool. And there are also other redundant inter-process communication. There is extra overhead, as well as wasted capacity on heterogeneous infrastructure if you're not utilizing the cluster to its fullest extent. Which means that if you see in this example, we have a variety of instances in there. And when you submit a job to the cluster, you do so using Spark Submit, and you specify the number of executors. In this case, we are showing 21. And you also have to specify the cores as well as the memory in order to optimize your job for that cluster. Now, we introduced something called dynamically sized executor. And this is where this feature helps you not to worry about right-sizing your cluster in this scenario with heterogeneous EC2 instances. So using dynamically sized executors, you no longer have to specify the static number of executors when you launch your Spark Submit job. So EMR sizes the executors for the available capacity on each instance. And so it will optimize for resource allocation, and it will improve your performance improve your performance of your job. It also reduces wastage, reduces the overhead, and also reduces the inter-process communication as a result of this uneven set of instances that you have. And most importantly for a customer, this means that there is one less decision for you to make. So we also introduced something called additive increase multiplicative decrease, AIMD for short. It's a strategy that we have implemented in order to optimize your writes to S3 at scale. And what this means to you is if you are running large-scale applications with S3 as the storage, we often see that these large workloads can experience throttling from S3. And when the data is distributed unevenly, you find this throttling problem more prominent. And so S3 learns from these data access patterns and automatically adjusts and scales over time. But how do we ensure that your immediate job does not fail? And to do that, EMR came up with these retry strategy. So on the EMRFS side, which is our native S3 connector, we have introduced a new feature this year called the AIMD strategy. And what it does is it reduces the throttling by up to 90%. So the way it does that is it's a feedback and control algorithm that we have implemented, best known for its use in the TCP congestion control mechanism. So we have implemented a similar strategy on Amazon EMR in order to reduce your throttling. So this chart here shows a benchmark that that writes about 800K of small files, and each file is about 1K in size. And we have run some tests using these 800 files on 16 C5 9 extra large nodes. And what we have noticed is when we ran this on this EMR cluster using multi-part uploads with this strategy, we observed about 90% reduction in S3 throttling, as well as some gains in throughput. Amazon EMR runtime for Apache Spark is a performance-optimized runtime environment for Spark that is active by default on Amazon EMR. So for those of you who are already running Spark workloads and EMR, you must be familiar with the Amazon EMR runtime, which has been, every year we run some TPCDS benchmarks to test the performance against open source Spark, as well as our own previous versions. And to evaluate the performance improvements, we ran this TPCD 3 terabyte scale benchmark on a 6-node C4 8 extra large using versions 6.4 and compared it against the open source version of Spark with version 3.1.2. And what we noticed is we got a 3 times faster performance based on the geometric mean that we calculated, as well as 2.7 times faster on the total time of running these queries. And most importantly, the EMR Spark runtime, the optimized runtime that you get out of the box is 100% API compatible with your open source Spark APIs. So as I mentioned, we also performed the benchmark against the previous release. So here I'm comparing EMR 6.1.0 with 6.4.0. And what we observed here is we got a 1.3x faster between these two versions on the geometric mean in 2021, and up to 4.8 times faster on the individual queries themselves. So the point here is that every year we make these enhancements and run these benchmarks to improve the performance of running Spark on Amazon EMR. So when it comes to a data engineer, they also are running CDC pipelines and other transactional data lake workloads extensively. So when it comes to running transactional data lakes, there are a few patterns that we noticed out in the field. The first one is streaming ingest pipeline. And when you look at the streaming ingest pipeline, it looks something like this. You have a mobile client or API clients that are sending telemetry data into a streaming service such as Kafka or Kinesis. And then you have a Spark streaming job that is ingesting data that's running on Amazon EMR and then ingesting data from this Kafka topic, and then putting it out in the S3 data lake for consumption. Now, there are certain challenges in this streaming ingest pipeline. The first one is trying to make an atomic change. What that means is You are sending in real-time streaming data, and you want your changes to be atomic. You want the readers and writers to be isolated from each other, which means that as the writes are happening, the readers should see only the committed or the compacted version. You also have situations in real-time streaming scenarios where you need high throughput ingestion. And last but not the least, there are, in almost all streaming cases, you have streaming messages that are really tiny. And when you have tiny files, it's a problem. And so you need to compact those files on a regular basis. So small file compaction is also a challenge that many of our customers encountered. And so, and this is not just for the ingestion, right? We also have similar problems or challenges when you want to query your data that is being sent to S3. For example, you only want to query the newly written data to your table. That's the incremental query. You want to know how your data looked at a point in time in your data lake. You want to have multiple engine support. Suppose you are writing your data into S3. You want multiple engines to be able to read the data and run their queries effectively. And then again, the second pattern that we see out there is the Cdc Injection Pipeline. And here you have data coming in, or the change data capture data coming in from a variety of RDBMS in your on-prem environment or on AWS. And you are consuming them using Amazon Data Migration Service to pushing it to S3, and then you're running some data processing jobs on EMR, and then the updated data is sent to S3. And this process has its own set of challenges. And they include, again, similar to the earlier case, you want your changes to be atomic, you want the reader-writer isolation, you want high throughput ingestion, you want the small file compaction, and most importantly, as this is a transactional data lake now, you want row-level upserts and deletes. You want clustering by secondary keys. So all these are some of the challenges that you really encounter in a CDC pipeline. And the third pattern that we see is from data compliance, like GDPR or CCPA, where you want to be able to do row-level updates and deletes, as well as support concurrent writes into your data lake. So this is where Apache Hudi comes into picture. So we have a number of customers using Apache Hudi in the last couple of years to allow for a transactional data lake. So due to the deep and broad scale of AWS, we have helped a number of customers implement transactional data lakes using the Apache Hudi. So let's take a look at what Apache Hudi offers and how it solves those challenges we spoke about for ingestion. So in terms of ingestion, as I mentioned, making atomic changes was challenging. Hudi offers transactions or the ACID capability that allows for not only performing reader and writer isolation, but also have concurrent writes supported. You have record level upserts and deletes. You have high throughput streaming ingestion, and it supports engines such as Spark, Flink, and Java writers. So you can write your applications in these in any one of these frameworks and consume data or write your Hudi tables. And most importantly, it allows automatic compaction of small files. So these are all some of the challenges that Hudi side solves on the ingestion side. And then when it comes to the query part, you can run your queries against Hudi tables using Spark, PrestoDB, or Trino, and we also have Hive support available to read Hudi tables. The queries are run efficiently across partitions and files, and this is because of the way Hudi indexes your records within S3 partitions. That makes it very easy to find or locate the records and the files that your query is interested in. It has incremental query support, which means that you can only look at the incremental changes that have occurred on your data between since the last commit, and you also have the ability to do time travel with Hoodie, which means that you can go back in time, look at how your data looked like at some specific point in time in the life cycle of your data lake. So the other things that Hoodie offers from an administrative perspective is that Hoodie asynchronously performs background file compactions. And it also does the background key sorting as well as clustering asynchronously. And it automatically cleans up files beyond the retention period. So there's this asynchronous process happening that automatically takes care of this, so you don't have to run extra pipelines to do these jobs. And most importantly, you have metrics for the past commits or rollbacks so that you can take a look at how Hoodie has merged your data. So, and this is available from the CloudWatch integration that we have available on Amazon EMR. So you can easily operationalize the entire Hoodie pipelines at scale using the detailed metrics emitted from your Hoodie applications. And running your data pipelines from a data engineering perspective are as simple as running SQL statements. So here we show an example of how to create a Hoodie table and upsert into a table. So there are more examples. We have more workshops as well as notebooks out there that go a lot deeper into how you can write your Hoodie programs. And most importantly, Hoodie is widely supported on AWS. So we started to support Apache Hoodie on EMR, and then soon we have had a number of other AWS services start supporting Hoodie as well. For example, the AWS Glue catalog and ETL support exists for Hoodie, so there is a connector that you can use with Glue today. Lake formation fine-grained access control is also supported with your Hoodie tables. We have Amazon Athena. You can use the Athena engine to query Hoodie tables, as well as Redshift Spectrum. So for those of you who have been running Hoodie workloads must be familiar with some of these requests that came from you, and these services have added support to enable querying Hoodie tables effectively from those engines. We have also integrated DMS for Cdc ingestion, and we have CloudWatch integration so that you can look at the metrics and act on how the metrics, the results of those metrics. Another important aspect of a data engineer is the ability to have multiple deployment options. So sometimes they want to run streaming jobs, sometimes they wanted to run bad jobs, and sometimes they want to run cost effectively on saving money for test and dev environments. And they do that very easily using EMR on EC2. But we also have Amazon EMR on EKS. And this is super helpful if you have an environment with Kubernetes clusters and you want to consolidate your Spark workloads into your Kubernetes environment and be able to run data processing on EKS. So Amazon EMR on EKS really simplifies your infrastructure management because there are no more clusters to build specifically for your analytic workloads. We containerize the Spark runtime so your applications can run quickly on any of the EKS clusters. This allows you to run multiple versions of Spark on the same cluster and allows you to build a security model that is very specific to a job. You can also have your teams stay agile by making quicker updates to both the application and the runtime. So on the same Kubernetes cluster, you might be running 4 different versions of Spark. each with its own set of security controls. You'll also be able to consolidate resources into a single cluster and improve the overall utilization of your Kubernetes cluster. And this consolidation often drives cost saving for many of the customers that we have seen in the field. And even if you want to simply take your existing resources and pull them into a single EKS cluster, you should be able to reduce your cost to get more work done, as illustrated in this example here. So if you have a need for faster upgrade cycles, as well as you want to run applications on a single AZ or across multiple AZ, this is a fantastic option. When it comes to submitting jobs to an EMR cluster or EMR on EKS, you have multiple options. So you can do it using CLI or SDK. You can connect to an EMR on EKS cluster from your studio, self-managed notebooks. You can use Apache Airflow, and you can also use step functions. So the example at the bottom shows how you can run a CLI command in order to start your job on an EKS cluster. We have also introduced the concept of custom container images, and this is where you can install and configure packages specific to your workload. So on the right-hand side, you see a specification for your image, and you can set your environment variables, you can install your favorite packages, and then incorporate your data pipeline into CDCI using custom container images. And this is very simple. You just pass in the container image when you're submitting the job, and your job will be run on that custom container image that you have specified. EMR on EKS also supports the concept of pod templates, and a pod is nothing but a group of containers that are brought together on specific properties such as compute and network isolation and things like that. And what you could do is you could schedule your Spark executors to run on Amazon EC2 Spot instances or Graviton instances with pod templates. And this is what it enables. You can run a separate service, like a sidecar service or a sidecar container next to your Spark driver or executor. And logging and additional monitoring are examples of other sidecar services that you want to run. You can also run an init container that prepares the environment. For example, if you want to run a container with specific jars or specific applications that you want to run before you start your job, you can do that as well with pod templates. And finally, we come to the administrator and Carlos, and how Amazon EMR enables Carlos to manage data lakes, security, and cost, to monitor health and the performance of the data systems like the clusters. So when it comes to an administrator is primarily concerned with maintaining the clusters, launching clusters with certain specification and managing them. And so when it comes to deploying the right EMR for their application, an administrator has a choice. He or she can either run Amazon EMR on EC2, where the administrator has the flexibility to choose instances that offer the best price performance for your workload, or they can go with Amazon EMR on EKS. Now, if an organization is running Kubernetes clusters and they want to automate provisioning management as well as scaling of your Apache Spark jobs on EKS, this is the choice that the administrator has. And just this week, we released a new deployment option called Amazon Emr Serverless, where you can run your applications using open source frameworks like Apache Spark, Hive, and Presto without having to configure, optimize, or operate, or even secure your clusters anymore. So this is a new deployment option that came out and is in preview right now. So if you want to give that a try, please visit our preview page and sign up for a preview access. And we also support running Amazon EMR on AWS Outpost. So this is where you set up, manage, and scale Amazon EMR on your on-premises environments, just as you would in the cloud. So from an administrative perspective, he has a choice of the deployment option, and the administrator can decide based on their organizational requirements. And lastly, we come to the cost optimization. Now, cost optimization is important to clusters because to customers, because they run big data processing jobs on petabytes of data. And so EMR provides configuration options that control how your clusters are terminated, so automatically or manually. So if you configure your cluster to be automatically terminated, it is terminated after all the steps are executed on that cluster, and this is what is the transient model for EMR, right? You run your job and you terminate the cluster. So Amazon EMR pricing depends on the instance type and the number of Amazon instances that you have deployed and the region in which you launch the cluster. So on-demand pricing offers you the lowest rates, but you can further reduce the cost by purchasing reserved instances, especially if you're running streaming workloads or workloads that need to run continuously. This is a great option. And finally, we have the spot instances. So spot instances can offer significant amount of savings. So you can go as low as 1/10 of the on-demand pricing in some instances. And the instance fleets configuration for a cluster offers the widest variety of provisioning options for your EC2 instances. So with instance fleets, you can specify a target capacity for on-demand instances and spot instances, and within each fleet, and when the cluster launches, Amazon EMR provisions instances until the targets are fulfilled. And then you can select multiple subnets for different availability zones. So when EMR launches these clusters, it looks across all the subnets to find the instances and purchasing options that you specify. So there's a lot of capability that we have built into cost optimizing your cluster environment. And so you can also containerize in order to consolidate on your analytics and save costs that way. We launched support for Graviton instances that have the best price performance within their instance families. So compared to M5, the M5G instances using Amazon EMR 5.30.1 have given us a performance gain of about between 12 to 16% when compared to non-Graviton instances in the same family. Similarly, you can reduce or lower your costs by up to 20% with Graviton instances. So overall, we have seen up to 30% better price-performance ratio. So spot instances are perfect for EMR because the nodes can be configured for a mix of on-demand and spot instances. You will find the highest capacity instances at the lowest price, and Spark on EMR adds additional resiliency to handle spot interruptions gracefully. We have talked about it extensively in the previous reInvents, and this is something a lot of our customers have come to like about the EMR, using EMR with spot instances. So here is an example. If you have 10 instances that are running on demand, and each instance is about $1 an hour, and you ran them for 14 hours, your cost would be $140. But if you add 10 more nodes from the spot market, you now have a 20-node cluster running for 7 hours, and the cost for those 7 hours would be $70 because you have 10 additional nodes running for 7 hours. And then for the spot instances, you have they're half the price, so you end up with half the price for the on-demand. And overall, your cost now comes to $105, which is much less than $140. So with Amazon EMR spot instances, you have a lot of flexibility in terms of reducing your costs, and it gives you a nice option to run your EMR clusters cost effectively. So we are almost at the end of the session. So here is a summary of the security. In conclusion, we want to say that we have implemented a number of features that enable all these personas to effectively run their EMR clusters. Thank you. I'll be happy to take your questions outside the room.